Hello friends, this video on D and F block elements part 19 is brought to you by examfear.com. No more fear from exam. Now we'll talk about the solubility or stability of the higher oxidation state. I've already told that this transition metals actually forms higher oxidation state with oxygen, with fluorine. Why oxygen and fluorine are electronegative, high electronegative and small in size? So you get higher oxidation state of transition metal when these transition metals are binded to fluorine or oxygen. For example, CrF6. So here chromium has +6 oxidation state. If you talk about the +6 oxidation state of chromium, it happens with fluorine. Let's talk about the manganese +7 oxidation state. So this happens when you talk about MnO3F. So if you see here, this has +7 oxidation state. Okay. For vanadium +5 oxidation state occurs with VF5, again with fluorine. Correct? Why? Because ability of fluorine to stabilize the highest oxidation state is because, again as I told, higher bond enthalpy and higher lattice energy. The main reason is it is very highly electronegative. It tries to suck electron toward itself. This delivers positive charge and actually you can get the higher oxidation state. And also the fluorine size is small, so the lattice energy is very high and the bond enthalpy is also very high. Okay. Also note that the fluorides are actually unstable in their low oxidation state. For example, VF2, this is unstable, but VCl2 is stable. This one vanadium has +2 oxidation state also, but VF2 is unstable, but VCl2 is stable. Okay, so fluorides and oxides, they need higher oxidation state for stability. Okay. If you see the copper example, copper 2+ is more stable, but as I have seen you, copper solid to become copper gas, you need atomization energy, then you need ionization energy to become +1, and then you need further more ionization energy to become +2, but still this is more stable than this. Why? If you see here, copper 2+ is more stable than copper 1+. Why? Because the hydration energy of copper 2+ is much more than the hydration energy of copper 1+. And that's why this is more stable. Because all this energy which is required is actually compensated by hydration energy. So if hydration energy is more for copper 2+, that will become more stable overall. And if hydration energy of copper 1+ is not that much overall, then this will not be stable, because overall it depends on delta hydration energy minus sum of all this energy, delta H, ATM plus IEs. So if this is very high, overall it becomes higher. Okay, and please note, out of oxygen and fluorine, oxygen has more ability to stabilize the highest oxidation state. For example, with Mn, if you see MnF4, at the max you get +4 oxidation state only with magnesium. But if you see Mn2O7, so in this case magnesium has +7 oxidation state. So oxygen has more ability to form higher oxidation state. Okay. Why? Because oxygen has the ability to form multiple bonds with metal. Fluorine can form only one bond, but oxygen can form multiple bonds with the metals. So higher oxidation state, oxygen and fluorine, oxygen has more tendency to form higher oxidation state than. So the question is, how do you account for the increasing oxidizing power of this series VO2+, Cr2O7 2-, and MnO4-. So let's see the oxidation state of this VO2+. Oxidation state is +5, Cr2O7 2-. This is 14 minus 2, 12, 5, 2 plus 6. This is 4 to 8, 8 minus 1, 7. So these are the oxidation states of vanadium, chromium and magnesium. These. Now for vanadium, if you see, +5 is the only oxidation state. For stable oxidation state, for chromium, it is +6 and +3. So it can actually jump from +6 to +3. For magnesium, it is 7 and 2. So it can actually jump from 7 to 2. That will also be stable state. So if it jump from 7 to 2, then the change in the oxidation state is +5. If we jump from 6 to 3, the change in oxidation state is +3. And for VO2 plus, this is the most stable state. So even if it is, goes to +4, +3 or +2, that will be unstable. So this is already stable. So this will be the least, it will have least oxidizing power. Why? Because for this to have oxidizing power, these should reduce. Right? If it reduces, then only it can oxidize other. So if when VO2 plus reduce, it will go to the unstable state. It won't want to reduce. If Cr2O72 minus reduce, it will go to +3 oxidation state, and the change in the oxidation state will be 3. If MnO4 minus reduce, it will go to the next stable oxidation state, it is +2, and the change in the oxidation number will be +5. So it has the maximum change in the oxidation number possible. So it will be the highest oxidizing power. Let's see the reaction for MnO4 minus. For example, you take KMnO4, you react with sulfuric acid, you get MnCl2, and you get KCl, and you get water, and you also get chlorine gas. Write the balance reaction. This is the balance reaction. Yeah. Now if you see, Mn had oxidation state of +7, Mn has oxidation state of +2, right? Both are stable actually. So +7 to +2, 5 oxidation number change. So it is a greater oxidizing agent, right? Same thing, let's see for chromium. K2Cr2O7 will actually react with again 14HCl to give 2KCl plus CrCl3 plus water and Cl2 gas. So if you see here, this is +3 oxidation state, this is +6 oxidation state, +6 to +3. The delta of oxidation number is 3. So it is little lesser oxidizing agent. We talk about vanadium, VO2 plus. It reacts with zinc, let's suppose, you get VO2 plus zinc is oxidized. So if you see it changes from +5 to +4. Only one oxidation number change. Also this is not much stable, this is more stable. So this will be a poor oxidizing agent. Correct? So if we have this chart where the list of oxidation states in the common oxidation state, you can actually infer a lot of information from this. Okay, this is dioxyvanadium. The next question is, how do you account for irregular variation in ionization enthalpy for the first and second series of the transition? So how do we account for this irregular variations of the ionization enthalpy in the first and second series? In the first and second ionization enthalpy, the first series. So if you see here, we have told that ionization enthalpy is directly proportional to the effective nuclear charge. Right? So the effective nuclear charge actually increase. Effective nuclear charge increase because of poor shielding effect of D, poor shielding effect. And also you are adding neutrons. So as you go left to right, you are adding neutrons, and also because of poor shielding effect, the effective nuclear charge is increasing. But then gradually you see that effective nuclear charge decrease because the shielding effect becomes more prominent, right? And thus effective nuclear charge decrease, and it is easy to pluck electrons, and these values, the first ionization energy actually decrease. You see here. Okay, for zinc, the electronic configuration is pretty stable. Zinc, it is 3d10, 4s2. It is pretty stable. It won't want to lose electron, and thus zinc has a very high value of first ionization energy. If we talk about the second ionization energy, let's see, this chromium has very high value and copper has very high value. Let's see the electronic configuration of chromium +1, right? Because this I am talking about chromium +1 to chromium +2 and copper +1 to copper +2. So let's see the electronic configuration of chromium +1. Chromium +1 electronic configuration, if you see, is argon 3d5 4s0, and copper plus, if you see the electronic configuration, it is argon 3d10 4s0. So if you see, this is full filled stable, this is half filled, this is stable. These are stable, so it won't want to lose electron, and thus it has high ionization energy. So ionization energy actually depends on my effective nuclear charge and also the stability based on half filled and full filled electronic configuration. Okay. Cobalt, if you see, it has a lower value of ionization energy. So let's see the cobalt electronic configuration. Cobalt electronic configuration is 3d7 4s2. But this is not giving any data. That means the cobalt also has this lesser value because of the better shielding effect by d orbital in the last elements of a particular series. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.